We're going to talk about some more limits that don't exist. In the last lecture we talked about left-hand and right-hand limits don't match. So we had, I think, the piecewise function, and we showed that from the left-hand side, for example, the y value was approaching 1, but on the right-hand side it was approaching 4. So we know that that limit doesn't exist when they don't match. The second one, let's take a look at the second one. We do a direct sub in here and we get infinity. But that's not a proof that it doesn't have a limit, because we don't, as we've talked about many times before, it doesn't matter what the actual value is, it just matters what it's approaching. So if we were to graph this one, and it's an easy enough one we can just sketch ourselves. If we were to graph this function, we know this very well to look something like this. As we put in really big values for x, it gets closer and closer to 0. As we put in very small values of x, or very small negative values of x, it gets really big, right? We put 0.2 or 0.1 in the denominator here. We get 5 or 10. It's getting very big very quickly. So you may say to yourself, well, we don't care what happens at 0, and to the left and right, it's approaching the same numbers. But the problem is it can't approach infinity, right? It can't be unbounded. So this guy is a DNE. It has to approach a real number, and of course infinity is not real. And infinity is ever increasing in a sense. Okay, so number 3, let's put this in our graphing calculator. So pause the video right now and put this in your graphing calculator, take a look at it, and then let's discuss it. Okay, so let's go to Desmos. And I've already put the function in, and this is what it looks like. So we wonder, is the limit going to be 1? Because it looks like on both sides of 0 here it's 1. Now remember, as we mentioned earlier, let me go back. Other numbers are fine. So if you say as x approaches, well, it depends. But let's say x approaches -3, for example. So as x approaches -3, right here, from the left and the right, it approaches the same value. And we could do a direct sub here and say that it has a limit. But at 0, something else is going on. Now it might look like it's approaching 1 here. But if we zoom in, right, if we zoom in, we see that it's actually going, now you can't see here because it's so compact, but every time it does this, it's oscillating back and forth. So it's going to 1, then it's going back down to -1, then it's going back up to 1, then -1, back up to 1, -1. It's actually never approaching a particular number. It's oscillating between two numbers, even if you zoom way in, which I'm going to attempt to do, but even as we zoom way in, it's always bouncing up and down. It's not actually approaching a particular number. So oscillating functions like this one also don't have a limit. All right? All right, the last thing we're going to talk about really quickly is finding some limits analytically. Now, direct sub is not new. We've been doing this for a while now. Remember, though, it doesn't matter what the value is at 3, but because there's some well-behaved functions like a polynomial or a rational expression that doesn't have a vertical asymptote, so anything like this, we can direct sub. Now, of course, you say to yourself, well, I don't really care what happens at 3, and I agree, but you have to remember that as a simple function like this, you put 2.9 in and you put 3.1 in, and it's going to be very, very, very close to whatever the value is at 3. So as long as this function is continuous and we're not having a piecewise function, for example, and it's a very well-behaved polynomial like this, all we have to do is plug in 3 and just figure out what the limit is, right? So this guy turns out to be 9, minus 6 is 3, plus 3 is 6. So the limit is really just 6, no big deal. So reducing rational expressions. So sometimes, as we know, these rational expressions have holes, which we covered in our pre-calc video. And the function I'm about to write here, right, is really the same exact function except for one thing. So let's talk about this, right? So the limit as x approaches 3, I'm going to do a different function. Now I'm just going to factor this. And right now it's the exact same function, I'm just in factored form. But when I go like this, I've actually got a new function, right? So now I'm asking the question, what is the limit as x approaches 3 of x plus 3? Well, that limit, right, this limit right here is an easy one when I ignore these two ones here, right? So it's just what? It's just 6. It's a well-behaved linear function. You plug in the number 3 and you get 6. Okay. You can't plug in 3 to this function here, but this function and this function, right, x squared minus 9 over x minus 3, and x plus 3 over 1, or times 1, is the exact same function except at the value of 3. So to the right of 3 at 3.01, it's going to give you the exact same value. And to the left of 3 at 2.99 or 2.9, it's going to give you the exact same value as 3.1. So we know that it's approaching the same number from left and right. Because it's a whole, the only difference is at that value of 3. But we don't care what the actual value of 3 is. We talked about this earlier in the first video with limits. So the limit of this function I've circled here, the original problem, is also 6 because it's the same exact problem except at one point, and that's the only point we don't care about. Okay, the next one is rationalizing. So if you do a direct sub into this function here, you're going to get 0 minus radical 2 over 0. And that's not going to be a real answer here. So what we can do, though, is we notice that this, right, can be changed by, I'm going to erase the equal sign here, multiplying by the conjugate. So let's see what that would look like, right? So imagine that's a parentheses, and I'm going to multiply top and bottom because I can't change the value of the function, of course. But I'm going to change the form, right? So I'm going to multiply by radical x plus 2 plus 2, and that will eliminate the square root in the numerator, right? So multiplying by the conjugate sometimes, in this case it will, give us a function that can be reduced, just like this function, and we'll use the exact same rationale in number 2 to solve the problem. So let's distribute. Now this looks really complicated, but of course it's just like x minus 1 and x plus 1, right? It's a difference of 2 squares, or it's the result of factoring a difference of 2 squares. So what we're going to get is a difference of 2 squares. So we're going to take the first term and square it. So that's just x plus 2, right? That's the first term. We're going to ignore the inners and the outers are going to go away if we were to FOIL it, for example. And the last is going to be, oh, and this was square root, my apologies. Right, the conjugate has to be exactly the same except for the plus sign. So we're actually creating this perfect square root scenario here. So negative radical 2 times positive radical 2, of course, is 2, right? Negative 2, though, because it's the difference of 2 perfect squares, the difference of 2 perfect squares. And look what happens to the denominator. It's just x times this big ugly thing. I'm actually not going to distribute it. You could, but I'm not going to bother to distribute it. I'm not going to distribute it. I'm just going to leave it like that. Now, why is that important? Well, because this 2 and this negative 2 are gone, and I'm left with an x, right? So I have x over x times something, right? And what's going to happen when I reduce the x's, right? So in other words, I'll write it out. X over x times something. Well, we can reduce the x's, and it's just like the problem above now, where I'm reducing something to make a slightly different function that's exactly the same function except at 0, right? So now I can do a direct sub, and if I do a direct sub, it's 1 over square root of 0 plus 2 plus the square root of 2. So what do I get? I get equals 1 over 2 square root of 2's, right? 1 over 2. And you can rationalize this, but in calculus we really don't care that often when we leave it. Oops, sorry about that. We leave it just like this, which I can't seem to highlight correctly, so be really careful. Okay, last two are just 2 trig identities, so I want you to put these in your calculators, and they'll become very, very obvious. And we just usually memorize these. There's a proof for these, but we're not going to spend the time to do that. And we're going to use the result of these to do other things, right? So I'm going to give you a homework problem in a second where I want to substitute these values and see if you can come up with an answer. Meantime, pause the video, plug these 2 in your calculator, and see if you can come up with the answer. All right, so I hope you saw on the graph of this one, which I'm not going to do, you have in front of your calculator, this actually is equal to 1, and this one's actually equal to 0. You just have to memorize these two. They're sometimes on the AP exam. And we also use these to do harder problems where we substitute in, we use trig substitution to get this form somewhere in the problem, and then we can simplify it. So I'm actually going to give you one of those in a second. All right, so that's 4. There's one more called the squeeze theorem. We'll talk about that one in class separately. But these are 4 ways, one you knew already, to find limits analytically. Of course, you also have the method, sorry, these are numbered wrong, this is 4. You also have the method of putting in your graphing calculator, as I just did over here. And of course, memorizing these two is very, very important. Okay, so let's try 2 different problems. So the first problem I want you to try for homework is this guy. So copy this down into your notes or into Notability. And I want you to find the limit of this thing here as x approaches 0. You're going to use this for f of x. So this is f of x plus h as h goes to 0. So f of x plus h minus f of x over h. So that means you're going to take this function, of course, and you're going to plug x plus h in wherever there's an x. You're going to get the result of that. Subtract f of x, so subtract these 3 terms. Divide by h and see if you can come up with a limit for me using this function for f of x. Okay? And we'll go over that in class tomorrow. And the other one I want you to try is, oops. I want you to try to find the limit as x approaches 0 of tangent x over x. And I gave you a big hint about this one already. Tangent of x over x. And I want you to do a trig sub for tangent. I think you know that one from geometry, hopefully. Do a trig substitution and then use your previous 2 trig identities to solve this problem. And come into class tomorrow and let me know what you find out. Okay, that's it. I'll see you guys tomorrow.